Hi, welcome to Solidio Gloria Physical Chemistry. This is the second lecture of Statistical Thermodynamics, and we are continuing to the previous lecture. Now we'll talk about molecular partition function, and then we construct the whole partition function and utilize it to calculate or evaluate the thermodynamic properties. Especially we are going to talk about, we'll derive at the end of this lecture, we'll derive the formulation for equilibrium constant in statistical mechanics. Okay, so let's begin. Let me get the laser pointer. This is the kind of the last section or last view graph we have done. So this is the partition function for the system of ensemble, and Q, small q, is the molecular partition function. So there are N, capital N molecules, and then those molecules are distinguishable. So total or whole partition function capital Q is equal to 1 over n factorial and Q to the nth power. Then Helmholtz free energy, this is where we go from statistical mechanics to thermodynamical state function. So given Q, the A is given minus KT ln Q. So Q is replaced with this formula, Q to the n over n factorial. So in terms of molecular partition function, A is given minus KT ln Q nth power of over n factorial, and then this is logarithm here. So logarithm to the q nth power is that n minus kt here, so minus n kt ln q, and then we apply, well, before we apply that to that, then the denominator n factorial is to make it minus to positive plus, so plus kt ln n factorial. Now we apply the Stirling's formula for ln n factorial, then minus n kt ln q, then this is n ln n, then n kt ln n minus n, so minus n kt. So n kt is common here, so minus n kt, and ln q plus ln n minus ln q plus ln n minus n, which is ln e, so minus nkt ln qe over n. So this is the A in terms of molecular partition function Q. Then we make a derivative of A with respect to T with negative sign, which is entropy, and derivative of A with respect to V and minus sign, which is P. And then with this we incorporate into, well, of course this is directly from derivative with respect to the number of particle, number of molecule, and negative sign gives you the chemical potential, and which is this. And then we obtain G equals A plus PB. So A is here, and PB, instead of PB, we can put ideal gas equation, which is usually, you know, PV equal nRT. In terms of number of molecules, PV equal capital N KT. So you just add plus nkt term here, then minus nkt ln E plus nkt ln E, small e. So you just here. And the internal energy U equals A plus TS here, you just multiply with T and add this to A. So what you get is nkt square ln Q around T. Okay, so this is U, and H you can obtain from U by adding PV, but just the same as here, you just add capital N KT to the U term, so you get this. Yeah. So we've been here just in the last lecture. Okay, so today's lecture begin here. Okay. So we need to know the single molecule partition function. Then n molecule partition function is q to the n over n factorial for indistinguishability. Okay, so the total energy for a molecule is epsilon, which is the sum of translational energy, vibrational energy, of course those are molecular, and molecular rotation energy, molecular electronic energy, I'm not sure what this N, which is a molecular nuclear energy. So, and these kind of degrees of freedom, translational degrees of freedom, vibrational, rotational, electronic degrees of freedom, and nuclear degrees of freedom. And this, with the kind of similar concept of Oppenheimer approximation, these degrees of freedom or molecular motion or molecular energy contributions are not coupled. So they are completely separated. And that's the first approximation. And these various kinds of energy of molecule are independent, or you can evaluate them separately. So you can evaluate the translational energy and vibrational energy, rotational energy, electronic energy, nuclear energy, all separately. And as a first, in chemistry, we're not really going into nuclear energy. So for this matter, we have just a photon, translational, vibrational, rotational, and electronic. So these four kinds of energies are summed to give total energy. So total energy is a sum of vibrational, rotational, electronic, and translational energies. And then if we separate these energies, then the partition function is a product of each individual translational, vibrational, rotational, and electronic partition functions. So Q, molecular partition function, is a product of translational, vibrational, rotational, and electronic, and all of those given as I would say Boltzmann vector. So e to the or exponential translational energy over kT, but total energy itself is translational, vibrational, rotational, and electronic energy. Okay, so the total energy over kT of that exponent, and then each has its own kind of degeneracies. Okay, so now the molecular partition function is decomposed to translational partition function, vibrational partition function, rotational partition function, and electronic partition function. And then the summation index, because the various kinds of energy of a molecule are considered to be independent, so we can apply the summation index separately for those degrees of freedom. So firstly, we do that for the translational energy and vibrational energy and rotational energy and electronic energy with a separate independent summation for the translation, for vibration, for rotation, and for electronic. So total molecular partition function is a product of translational, vibrational, rotational, electronic partition functions. Okay, so this is the partition function for a molecule. And then for the system, there are n number of molecules. Total number of molecules is capital N. So Q is these separate term partition function for the molecule, Qt, Qb, Qr, Qe to the nth power over n factorial. This is the canonical partition function for ideal gas. Okay, each ideal gas molecules has internal degrees of freedom of vibrational, rotational, and electronic. That's it. So with this in mind, with this total canonical partition function, the thermodynamics of it is A equals kT and Q. Then we are going to make a logarithm of this Q And then for kind of convention, we include this indistinguishability part, or 1/n factorial, into the translational. Yeah, because the molecule total itself is not kind of distinguishable. So that's quite reasonable. So first term is minus KT ln Q to the n Qt to the n of n factorial. And second is that minus KT ln QV nth power, just like that. But n is the exponent, and we are going to put ln log here, then n goes in front of the log sign. So first term, the Qt, is then minus nkt ln Qt, and then we apply for ln 1/n factorial, which is minus ln n factorial, and then we apply for the Stirling's approximation to that, so we obtain this. Okay, and then for the rest, QV, QR, QE is done in this way. So minus nkt ln QV, minus nkt ln QR, minus nkt ln QE. So vibrational, rotational, and electronic molecular partition function. Okay, so this is A. Once we obtain A, we can get all other thermodynamic state functions. So we'll do firstly translational contributions to thermodynamic properties. So now we consider the volume in a cubic box of V. So molecules are in a cubic box of volume V, and then one length of the cube is V to the 1/3 power. Right? That's the way we are going to handle this. And then if this is, you remember that particle in a box problem, okay? And the box is the cubic box, and then the volume is V. That's what it is. Then there are 3 degrees of freedom, or 3 dimension partition. The wave function we would obtain. The energy has 3 quantum numbers. So those 3 quantum numbers for each direction, nx, ny, and z. And then the total energy is, you remember that n square h square over 8m a square. A is a kind of length of the box. Okay, so then in this case, the length of the box is that 1/v to the 1/3 power. So now we have 8 times m v to the 2/3. Okay, 1/3 square. And then the energy is that numerator is that n squared times h squared. So each direction has nx, ny, and z. So nx squared plus ny squared plus nz squared h bar squared. This is the total energy of the particle in the cubic box. And then this is one molecule. So one molecule. And then translational partition function for one molecule is, now you are going to sum over all energy state. So you are going to go from nx, ny, and z summation nx equals to 1 through infinity. 1 through infinity, just like that. Now in this case, you can do 0 through infinity except just 1. So basically that's what this summation is going over. And then this is this. So then you can separate these terms, because this is the exponential, and then some of the exponential could be break into the exponential times product of exponential. So that is done here. So you do this. You do this for each summation index, and summations are separated by these 3 independent summations. And then nx, ny, and z in this case is a dummy index, and then you can treat it as just 1, n equals 1 to infinity, then this to the 3rd power cube. And then we consider that T is rather Well, the energy itself is n squared times h per square, h squared in this case, is much greater than kT, unless the t is very small. So in ordinary situation, like dealing with at room temperature, this is not humongous compared to n squared h squared. So we can consider this is very small number. So small number. So what I mean by h squared over 8mv 2/3 and kT is very small. Then the separation between the index, like n equal 1, n equal 2, and then the distance between n equal 2 to n equal 3, like that, is very small. So we can consider that as continuous variable. And so this is replace the summation with the integral. So that integral would be 0 through infinity e to the minus n h squared n squared, just like this, and just over all this 8mv 2/3 kT. And but you replace this summation with integration, integral 0 to infinity dn. So if you integrate this in this range, you get this. So 2 pi mkt square root and v 1/3 over h, and then you have 3 terms. So what you have is that all this cubed, that's qt. T. Okay, so you make this all this together into this one kind of constant terms, 2 pi mkt over h squared over or that 2/3 3 halves power, and then v is just independent over here. Okay, just v. And then what we can define here is lambda. Lambda is the thermal wavelength. So depending on the temperature, we can consider that motion of the particle as a wave, and then the wavelength of that molecular motion is the thermal wave for the temperature. So what we have here, we define this as lambda cube. Then lambda is h squared over 2 pi mkt square root of this. That's thermal wavelength. Then maybe we can calculate the thermal wavelength and how long it is for a molecule. So example here is that molecular partition function for the translational motion of hydrogen at that temperature, 3000 K, and the volume, this is smaller volume for that, I think, about this temperature. So like 24.94 liter, or 0.2494 the cubic meter cube. And then it asks us that calculate thermal wavelengths. So the partition function is this, and thermal wavelength is the v over lambda's cube. So firstly you obtain this, and then divide by the volume, and then make a cubic root, then we obtain the lambda. So qt, so 2 pi, and this m is the weight of the hydrogen atom, but in this case we are going to use per mole, and then we can use this k per mole. Yeah, so we use this as 1.008 times 10 to the 3rd kilogram per mole, and then we are going to use this is the Boltzmann constant, and then this one this is the molar quantity, so we divide by Avogadro's number per mole. So this is then what we get for this and this together. What we get is the mass of the hydrogen atom, and then we use just a molecular gas constant, which is the Boltzmann constant here, and then the temperature 3000 K, and then we put this H for the Planck constant, and then the volume is as it is here. The volume is given in meter cube, and then kilogram meter cube. What we get is in joule. Joule is here. Okay, so those are kind of cancel. So the QT, the partition function, doesn't have a unit. Okay, so get these all into your calculator. It will yield you 7.791 to the times 10 to the 30s. This is the molecular partition function for the hydrogen atom at 3000 K in this volume. And then wavelengths, thermal wavelengths is just this. Well, actually, thermal wavelengths is this quantity and a cubic root of this quantity. So what we get is that the V divided by this QT, then that's 1 over lambda cube. So no, sorry, lambda cube is that V divided by QT. So we make that cubic root, and then obtain this. So about 3000 K, at 3000 K, the wavelength of a hydrogen atom is this amount of meter. So you recall that 1 to the 10 to the minus 10th power of meter is on 1 angstrom. So this is about 0.3 angstrom. And then the hydrogen atomic size is about angstrom. So which is so the wave, thermal wave is about 1/3 of its size, just like that. And then what we are going to do is, once we have, it says a translational contribution to the thermodynamic, other thermodynamic properties, once we obtain A, and then in terms of V and T, then we can obtain all others, just what we learn as what we learned from thermodynamics. So monatomic gas like hydrogen atom, it does not have no internal degrees of freedom. So translational partition function is just a total partition function for the atomic species. So Q itself is, then now you have this 2 pi mkt over h square 3/2 power, and V is the molecular partition function. And then what we get, the total partition function for n molecule or n atoms is 1 over n factorial, and that to the nth power. So Q is here, and then we can make minus KT ln Q, which will give us translational Helmholtz free energy, and which is on like just to put these into ln, and then it gives us this, and then now because this is minus ln n factorial, then what we do is minus n ln n plus n, which is done here, and then that gives us this. And then V O N, what we do here is this relationship, PV equal capital N KT, or PV equal small n RT, the ideal gas equation. So instead of here V over n here, then what we do is that P over KT. So P over KT is just V over n. V over n, P over KT. V over n is P over KT. P over V over n. V over I'm sorry. V over n is the kind of n over V is P over KT. So V over n is KT over P. So KT over P instead. So that's how we obtain this. We will repeat this several times at least today. And entropy is the same relationship from the fundamental equation, which is dA is equal to minus SDT minus PdV. Okay, so what we do is that just the derivative of A with respect to T minus will give us the entropy, and derivative A with respect to V minus will give us pressure, and that is done. And then especially for S, T is the Sackur-Tetrode Equation. We just use this and that kind of downward. Okay, so there are some more. So once we have these, and then what we did obtain was T and S and P, and then we did, and of course we can do this make a derivative of A with respect to N. We'll obtain the chemical potential for the natural variable T and V, so which is on here. And then now we know A and T and S, we can obtain U. And once we know U and also P and B in the previous slide, we obtain H. And then, otherwise G is obtained H minus TS, or just this is molar quantity, so we just obtain the number, then we obtain G. G is here. And then for this thing, what is the heat capacity? Heat capacity is a derivative of U with respect to T. Now this is very simple. What we obtain is 3/2 of NK. Okay, 3/2 NK, 3 NK over 2. So this is it. And here we can consider, or we'll look for Equipartition theorem, which is in the classical view of Equipartition theorem is that each square term in classical energy expression, for example, kinetic energy is 1/2 of m times v square, but v square is vx square plus vy square plus vz square, just like that. So translational energy, and then what the Equipartition theorem tells us that each 1/2 m something square contribute 1/2 of r to the molar thermal capacity, heat capacity. So what it is that each square term in the classical energy expression for a molecule contribute 1/2 of r to molar heat capacity at constant volume. That's the catch, constant volume. So we in the previous slide we talked about the constant volume heat capacity, which was 3 nkt over 2. So because there is x and y and z degrees of freedom, so that's for the kinetic energy. And then translation, meaning translational energy. So the contribution to the molar heat capacity for each 1/2 some x something square was 1/2 r. So there are 3 terms. So it was 3 r over 2. Actually, it was 3 nkt over 2. So rotational degrees of freedom for the rotation, each rotation is expressed by 1/2 I omega square. I is the moment of inertia and omega is angular velocity. So each angular velocity contributes to 1/2 R. And vibrational degrees of freedom case, the vibration, which is the kinetic term and also potential term. So potential energy is 1/2 of kT, kx square in one dimension, and x in x, and then kinetic energy is 1/2 mvx square. So for vibrational energy or vibrational degrees of freedom, there are 2 terms in something 1/2 x square or x, or 1/2 vx square. So it has 2 terms. So each degrees of freedom, vibrational degrees of freedom, contribute r. So 2 times 1/2 r. So these are kind of decomposition of energies. I mean kinetic energies or potential energies, but each 1/2 potential or kinetic square term contribute each by 1/2 r. But next time, or in the next couple of slides, we will calculate or evaluate that energy, kinetic energy, that energy meaning is rotational energy or vibrational energy or translational energy compared to kT. It's a kind of thermal measure. But here what it says is the translational or rotational energy is small compared to the thermal measure, but this is rather big or large compared to that thermal measure of the energy. So this is not vibrational degrees of freedom, is not, especially this one, potential term is big compared to thermal contribution, so it's not fully activated. That's what it says. So these, including vibrational, compared to translational, rotational, or it says that translational, rotational, vibrational whole only active, satisfied only at high temperature limit. So because of this, the heat capacity depends on the temperature. So the heat capacity varies as a function of temperature. And then there was a Sackur-Tetrode equation we just looked a couple of slides ago. So we now apply a Sackur-Tetrode equation to evaluate the entropy, translational entropy in this case. So molar entropy of an ideal monatomic gas, just we've done for the hydrogen atom, as a temperature T and a pressure P. So in the case T Kelvin, P bars. So ST, translational entropy is NK ln 2 pi mkt over h square to the 3 q's. I'm sorry, 3 over 2, and then which has another term kt e to the 5 power over p. So we'll calculate this as a function of t and p. So what we did is t from here to 98K to 1000K. So here is about 200K. So 200K. Yeah, 200K. I'm sorry. This one unit here. One unit is 400. Yeah, 200. So this is about twice of 200. So let's say this is 298K. Yeah, and then goes to 1000K. So T axis here and pressure axis is 1 to 100 bar. So 1 is around here, and then 0 is here, and 100 bar. So as a function of P and T, we calculate the entropy, translational entropy with the Sackur-Tetrode equation, and then it's done and it's plotted in 3D. So here, so as molar entropy is this as bar, then we are going to use this capital N with as Avogadro's number, or Na times K is R, so that's R here. And then also we break this separately into ln e to the 5 halves is 5 halves of 1, so it's 5 halves, and then ln up to this times kt over p. But here the technical way we look at it is that we use m, which is am nu. Then for that am nu we are going to use the atom mass unit separately. So AMU times atom mass unit. So there are 3 halves power. So it goes in front of ln. So it's done here. And also instead of P was P, but we are, because logarithm shouldn't have a unit. So P is given as just 1 atm, 1 bar in this case, and then it is separated out to just a P with 1 bar. In this case, the numbers given here, like 100 bar over 1 bar, and that's just 100. So that's done. Well, this is the kind of technical way we represent that. Also, T is just to put 1K, or just unit temperature, and then we put just to separate out, because that there is T 3 halves and just 1 is the totally T 5 halves. So we have this. So just like this, and then we incorporate these. Well, actually, we can just put these numbers and then calculate it, but just to make sure that not the numbers in the logarithm should not have a unit. So this is the way, and then those calculated here, and then just made the plot just like that. So the translational entropy increase as a function of T, as T increase, and also increase when, well, the volume increase, meaning is that pressure decreases. So we just confirm the trend. And then, so we analyze all the translational contribution to the thermodynamic state functions, and now we switch gear to the internal degrees of freedom. So atom do not have, monatomic gas do not have any internal degrees of freedom, but diatomic molecules, H2 and all other molecules, more than one atom, single atom, in the case they have vibrational rotation contribution or electronic contribution too. So firstly, we'll look at the vibrational contribution. So now we'll consider only diatomic molecule and vibrational, low vibrational quantum number. Okay. The reason for that is that this NKT, high vibration means the high vibrational quantum number. So we are not going to use very huge number here. Well, anyhow, if the contribution high vibrational, then which is much greater than, that would be greater than KT, then this term is very this to the exponent, so large exponent, negative large exponent, getting smaller contribution. But anyhow, so that's we are going to consider only the low quantum number, vibrational quantum number, and then which means that we can use vibrational state of harmonic oscillator to assign that vibrational motion. And then, well, and also the lowest vibrational state has the quantum number 0, but there is a 0-point energy, half of h ni. So, but we are going to set 0 of energy equals to that, meaning is that the 0-point energy considered to be 0 for the energy scale. Okay, so then the vibrational energy as a function of vibrational quantum number is epsilon n equals to n times h ni. You remember that vibrational energy was n plus 1/2 n times h ni. That this is what it means. The 0-point energy concept is set to 0. Okay, so that's what it is. Then, given the state, counting all the states, summing over all state from n equals 0 through infinity is summed, and that's the vibrational partition function. Okay, so this energy to the partition function. And then we would say that this is the sum, is a geometric sum, with the first term 1, and the ratio for each term is h nu over minus h nu over kt. So the sum is 1 over 1 minus r. So e to the minus h nu over kt is the ratio, and then this is the partition function. So vibrational partition function given in this single term for each mode. Okay, if there are number of modes, then you would have exactly the term like this with different frequency. So ni is the vibrational frequency. And then here we define Hni over K as the characteristic vibrational temperature. Then we have this single term like this, 1 over 1 minus e to the minus theta ni over T. So theta ni is Hni over K. So this is the characteristic vibrational temperature. So if you compute this one, then this is rather high. That's why the vibrational degrees of freedom is inactive at low temperature. So we only consider vibrational contribution at high temperatures. Okay. And then once we know the partition function, we can calculate the thermodynamic state functions. So firstly, we obtain Ni is meaning is by AV. Yeah, shall we call AV vibrational? This Ni is not V. This is the frequency. And also, if you have more than one normal mode, and then there is one vibrational quantum vibrational partition function for each mode. So total vibrational partition function is the product of all partition function for that particular mode. And then A is minus nkt ln q qv because the qv nth power, the n goes in front of the ln log sign. So nkt this, and then the qv is here. Then minus was go into the log sign, then makes this reciprocal. So we have this, and then we make a derivative with respect to t minus, and with minus sign gives us vibrational entropy, and the pressure of this is that we just make this derivative v, but there is no v dependency, and then there is just a vibrational pressure, is something like, and it's 0. Then of course then mu v is the make a make derivative with respect to n, and then which is this. So because we just make a derivative, there is no dependency in n, so nkt yeah, just nkt of this, and then t derivative, you make a derivative this and also derivative this. So there are two terms. Okay. And now we are going to do rotational contribution, and rotational energy for the diatomic molecule is just then there is two rotations, but there are two rotations, and but we are considering only one here. So the rotational energy and rotational quantum number is j plus 1 h square over 8 pi square I is the moment of inertia, and then the each j state has degeneracy 2j plus 1 for degenerate, because there is a this is rotational quantum number, this is directional S component, minus a to m quantum number from minus a to minus j to j, and all the integers in between. So there are 2j plus 1 state. And then for the rotational partition function, which is summation from j equals 0 to infinity, and then 2j plus 1 is the degeneracy, and then that's the energy, so the energy term. And then this j plus 1 h square over 8 pi square I k is very small compared to t. So this the total thing is kind of small. So could be considered for each j, could be considered kind of continuous variable. So instead we just this summation, we just to make a integral 0 to infinity, but dj, with respect to dj. So we integrate this from 0 to infinity. What we get is a pi square IKT over h square. And then again, we also obtain this with respect to t, so that as a characteristic rotational temperature. So each rotational energy makes kind of a fraction of the temperature, I mean the thermal energy, which is kT. So that's kind of comparison for that. So the theta r rotation, the characteristic rotational temperature is just like because this is kind of a reciprocal relationship, which is h bar square now. H theta is h bar square, h square, I'm sorry, h square over 8 pi square ik. Okay, so this. And then if there are many independent rotation, usually there are 3 rotation for non-linear molecule. So each, and then meaning is that those are indistinguishable rotation. The effective symmetry is considered, and then so those will be considered as considered with the symmetry number. So if I read it again, for indistinguishable orientations, the effect of symmetry is counted by symmetry number. Okay, so so the molecule has symmetry. So for rotation, those are kind of indistinguishable molecular shape is kind of encountered number of times. So those is considered, and then as a symmetry number. So rotational partition function is divided by the symmetry number. So yeah, so and then yeah, then Q total R is this divided by symmetry number. So QR is T over theta R times sigma, okay, which is the symmetry number. Now we are going to obtain vibrational characteristic temperature and rotational characteristic temperature for oxygen molecule in gas phase. So the difference is that we use just the oxygen's molecular property. Okay, so the vibrational characteristic temperature is HC d to the this is from how we obtain this vibrational frequency is from rotational vibrational spectroscopy, and then it reports the frequency in wave number. So instead we are going to use the wave number, which is this one. But usually the wave number is expressed in reciprocal centimeter, but here we are using joule and second is just the SI unit. So it is now given in SI unit per meter. Okay, meter and minus 1. Okay, so and this is the speed of light, and then h Planck constant, and then the Boltzmann constant. This is us to have 2273.77 K. So about 2200 K is the characteristic vibrational temperature. So at the room temperature experimental case, we don't see full activation of vibrational degrees of freedom. That's why we don't include that at low temperature calculation for fully included this vibrational contribution. Rotational degrees of freedom instead, h square over 8 pi square ik, and then we have all this. This is the inertia, moment of inertia of oxygen molecule, and then we get this. So look at this. This is 2K. So which is at room temperature, rotation is easily activated. That's what we know. Okay, but the polyatomic molecule, and so each rotation, if you see many indistinguishable orientation, you must consider that symmetry number for each rotation. But polyatomic molecule has at least, if not linear, it has 3 rotational characteristic temperature, because it has 3 independent rotation. So it says that at temperature well above the characteristic rotational temperature, most of case, unless it's very low cryogenic temperature, rotational partition function for a non-linear polyatomic molecule is given because it has 3 rotational degrees of freedom. Then, which is this, then and also the total symmetry number. So this is the rotational partition function. And then each characteristic rotational temperature for each rotational degrees of freedom, psi A, theta A, theta B, theta C, well, the same formula except that moment to inertia for that particular rotational exit, A, B, C. The symmetry numbers is the for each molecule equal to the number of distinct proper rotational orientation, which means that He2O, in this case, you see that the rotational axis C2, and for that rotation, there are 2 indistinguishable He2O orientation. You see, like this, and then if you rotate the other way, that those 2 are the same. And then for ammonia, it is 3-fold rotation, so null axis of sigma is 3, and for ethylene it's 4, and methane there are 12, because that each CH axis has 3 different indistinguishable orientation. So benzene case, benzene is 12. Okay, so this is what we have to consider, have things in account. And also for each methyl group, there is a factor 3 for symmetry number. So this you carefully figure out what's the symmetry number for the given molecule. Okay, the last thing about molecular internal degrees of freedom is electronic contribution. To the rule of thumb, electronic energy is much greater than vibrational, and also vibration is much greater than rotational energy. So electronic contribution, unless it is very particular special case, we only need to consider ground state. Okay? So this is that electronic energy of state I, electronic state I. And then we will, for the electronic partition function, QE is that we just sum over the kind of Boltzmann factor e to the minus epsilon EI over KT, and then GI is the degeneracy of the particular energy level, energy contribution. So, and then we are going to also we'll consider the characteristic temperature for the electronic degrees of freedom, and then which is that epsilon energy, electronic energy over K, which is really great number than vibrational or than rotational. And then we'll consider the degeneracy for the atom, and then which is kind of a orbital angular momentum, but it's kind of degeneracy or multiplicity of that electronic state. So QE for the electronic partition function is G0. G0 is the ground state degeneracy, and then that is the ground state is the energy 0, and then G1, that's the kind of this epsilon E1 is from above the epsilon 0, which is 0. Okay, so we obtain this just E1 and E2 just like that. So G1 is first excited state, G2 second excited state, so it's like, okay. And so as I just mentioned that this the electron excited state energy is very huge, so we only need to consider the ground state to calculate the partition function or enough contribution. And also for the excited state, the vibrational frequencies and rotational frequencies for the excited states is very different from ground state ones, so you need to figure out separately for the excited state. So rule of thumb is that if you most of the time you need to only include the ground state, electronic ground state, and then you can combine that to previous calculation like a vibrational and rotational contribution together. But when you need to include, there are some special cases or very high temperature, 1000 degrees of temperature maybe. And then if you are going to include higher level of electronic state into the partition function, and then you are going to figure out again, separately figure out the vibrational and rotational contribution in the electronic excited state, because those are not the same as the ground state one. Okay, so that's what you need to know. And also, we are getting close. Yeah, okay, this is the last topic. So I think we have done like about an hour now. So let's just bear with me a little more. I appreciate that. This is kind of the wrap up everything. So equilibrium constant. So we are going to calculate equilibrium constant. So the example here we are going to do is just a monoatomic gas and then diatomic gas. So it's a kind of a decomposition of diatomic molecule into the atoms. Of course, this is very simple reaction, but you can apply this to any complex chemical reaction. Well, of course, you can do also a simple experiment to figure out the equilibrium constant, but there are certain chemical reactions that you cannot perform in usual sense, like some reactions at the surface of the sun, like that 6000 K degree at the least. Okay. So those kind of things, this statistical calculation is very handy and helpful. So for the equilibrium constant, what we are going to use is delta G naught equals to minus LTLN K. This is a thermodynamic equilibrium constant, so you need to know this. So this is the standard Gibbs free energy. Okay, standard Gibbs free energy, and then molar Gibbs free energy is also GI over Ni as the molar Gibbs free energy. So which is minus RT. Now we are going to use this molar quantities and in general RTLN QI over Ni. And then this GI is GI naught plus RT ln PI over P naught. Okay. So instead, what we get, this is from here. This is multi ln. So what you are going to use this Ni is that NIRT is PIV. Okay. So what we get here, that this 1 over Ni is replaced by RT over B Pi Na. Na is the because this the Ni is from the ideal gas equation. Ideal gas equation is to Ni with these quantities, and then we make a separation in this quantity here in terms of P naught and Pi over P naught. Okay, so if you look at compare these two lines, and then you have this, and then this GI naught molar gives free energy for the species I is this, so which is minus RT ln QI of RT over VP naught over NA. NA is Avogadro's number. And then what you can do is separate out minus RT ln QI over V minus RT, and then all other terms RT P naught NA. Okay, so P naught NA. Yeah, here is the equation I used to obtain this NI instead. Okay, so once you have this, what you are going to use this one. Okay, so KT or K is summation of G I naught over RT minus. So K is the summation of this, but that summation has of these and that. Okay. So and also you divide by that. Okay, and then and also this. So you can treat these two terms separately. So firstly, you obtain this in order to make K, you divide by RT, and then that's ln K, and okay, that's ln K, and then that K is related to this, and then this is the kind of for each I you have this term, and then what we are going to use is that sigma nu I. This is nu is the stoichiometric coefficient for the reaction. Okay, so you have this one, and then for this one, for this term, you do the same, but ln is in this side, so this is a kind of a product of each. What is this? Is the stoichiometric coefficient. Okay, so this is done that way. Then of course this is R over NA is K, so just a simplification, and that's the same. So monatomic gas as QV is what you have here is that just the translational partition function, and of course there was a V, and which is divided by V, so it's gone, and also degeneracy of that electronic monatomic gas. Okay, so usually I don't know which is one, but anyhow, it's a electronic ground state for monatomic gas. And for diatomic molecular gas, which is the same for the translational, and then the electronic degeneracy, and then kind of the energy level between these. Okay, so the degrees of freedom, electron degrees of freedom of diatomic gas and monatomic gas. And then this is rotational partition function, and that is the vibrational partition function. This is ground electron, and the translational, and that's the electronic partition function. So molecular gas contains all these four contributions. Okay, so our example for that is this equation, this simple reaction. Hydrogen gas decompose into hydrogen atoms at the temperature 1000 K, and for hydrogen molecule we just use the harmonic oscillator and Rizzo-Otto approximation. Yeah, just that we have done. So the hydrogen atom, the electronic ground state is just 1s electron, and which is doublet. Yeah, just one spin. So G0 H is 2. Yeah, that's what it is. And it's a kind of a mass, and then mass per atomic mass. Then we can calculate QH over V as just an electronic partition function, and then the translational partition function over V. The V is gone. So that's 2 times 2 pi, and the weight, and K, T, and then the Planck constant square, and then 3/2 power, and then this is it. Yeah, this is it. That's the hydrogen atom's partition function. And hydrogen molecule case, which is that the ground state is that two electrons paired, so singlet, and then rotational case that the sigma is 2, and then rotational characteristic temperature, vibrational characteristic temperature, and then the hydrogen, well, actually dissociation energy. So dissociation energy into hydrogen atom, which is this one, about 432 kilojoule per mole. And then you can compute this to make this, okay, 3.6 10 to the 54th power, and that's 31. Then we can incorporate these together. We obtain this, and then KT over P naught, KT over P is a kind of a standard or reference pressure, but actually it's 1 bar, and then that number. So what we can do is K is now, because this relationship is partition function of hydrogen molecule, partition function for the hydrogen atom square, and this is 2 minus 1, so 1 is here. So stoichiometric coefficient is 2 minus 1. It's there. So what we get is times that square over that is 5.54 times 10 to the minus 18. So that's what we kind of calculate from ab initio way of hydrogen atom and hydrogen molecule, and then we obtain the equilibrium constant at 1000 K. I guess this is the end of the second lecture. I always appreciate your patience listening to this long lecture. So once you listen to this lecture and make your own note and put into your mind. Thank you.